last section in this chapter. We're going to take what we learned at the beginning of the chapter about conic sections and what we learned a little later on about polar coordinates, combine those two things together and see what conic section equations look like when they're written in polar coordinates. And we had some kind of clues when we wrote in rectangular coordinates about the pluses and the minuses and x squared and y squared that helped us figure out what kind of a shape we were looking at. Polar coordinates also have some little clues like that. So let's take a look. In polar coordinates, I have basically two equations. R is equal to ED and one plus or minus cosine theta, or the other equation that I might have is R is equal to ED over 1 plus or minus sine theta. Okay. Just a reminder, this E is the eccentricity, and it is always a positive number. Okay? And the D, we'll say the absolute value of D is the distance from the focus at the pole and the directrix. Okay. Earlier, we only talked about the directrix really when we were talking about parabolas, but there's also a directrix for ellipses and one for hyperbolas, and we'll look at that in this section. Okay, so if I have this equation, R equals 15 over 3 minus 2 cosine theta, that looks pretty similar to the format that we had. The one thing that's different is this is a 3 and it needs to be a 1. So to make this be a 1, I'm going to divide all the numbers by 3. So I'm going to have 15 divided by 3, 3 divided by 3, and 2 cosine theta divided by 3, which gives me now 5 over 1 minus 2/3 cosine theta. Okay? And this 5 then is equal to ED, and the 2/3 here, that's the eccentricity. So if 5 is ED and E is 2/3, all I have to do to find D is multiply by 3 over 2, and I get 7.5 is equal to D. Okay, the E equals 2/3 tells me when E is in between 0 and 1, I have an ellipse. So I know this is an ellipse, and I could plot some points to find the upper half and know that the lower half is going to be symmetrical to it. So in this case, my ellipse is going to look something like this. Let's look at another equation. We've got r is equal to 32 over 3 plus 5 sine theta. Again, I need this 3 to be a 1, so I'm going to divide everything by 3. This is not quite as nice as the last problem, but I get r is equal to 32 over 3 over 1 plus 5/3 sine theta. Okay, this time the e is 5/3, which is greater than 1, and tells me this is a hyperbola. Okay, and then d, remember d times e is 32 over 3, and I can replace the e with 5 over 3. D times 5 over 3. So that gives me that d is equal to 32 over 5. Okay, so we could say the directrix is at y equals 32 over 5. Okay, the transverse axis is at pi over 2. And my vertices are at 4 pi over 2 and negative 16 pi over 2. Okay, and I can use my same identities that I used before with A, B, and C to find the transverse axis, the conjugate axis, and the location of the foci. In our last example, we're going to look at the equation for the path traced by Halley's Comet and use it to find out just how close the comet gets to the sun, which is at one of its foci. So for Halley's Comet, we have an eccentricity of approximately 0.967, and the major axis is at 35.88 astronomical units. Okay, and an astronomical unit is defined as the mean or the average distance between the Earth and the Sun. So 35 of those, this comet goes way on out there. Okay, if we assume a vertical orientation for this ellipse, I can write the equation this way. R is equal to ED over 1 plus E sine theta. Okay, and in this case, the vertices of the ellipse would be when theta equals pi over 2 and theta equals 3 pi over 2. So let's say here's the sun, and we've got this long skinny ellipse, and here's pi over 2, and down here's 3 pi over 2. So I can write 2a is equal to 0.967 d divided by 1 plus 0.967 plus 0.967d over 1 minus 0.967. So that 35.88 is approximately equal to 29.79 d. So d is approximately 1.204, and ED is approximately 0.967 times 1.204, which gives us a final answer of 1.164. Okay, now we're going to put that number into our equation and say R is equal to 1.164 over 1 plus 0.967 sine theta. Okay, now R is going to be measured in astronomical units. So if I want to find the closest point to the sun, which is one of the foci, I could say that C is equal to E times A, which is approximately 0.967 times 17.94, and that's approximately 17.35, and then we can subtract A minus C would be the 17.94 minus 17.35, which gives us 0.59 astronomical units, which translates to about 55 million miles. But I can't spell miles. Okay, so that's the orbit of Halley's Comet.